Hi everyone, in this video we're going to be discussing inverse trig functions or inverse circular functions. Now in order to talk about inverse functions, we have to remember quite a few things we learned in algebra. So recalling when you first learned about functions and then their opposites or inverse functions, we're going to go through that and it's going to help us with our inverse trig or circular functions. Now first recall that for a function f, every element x in the domain corresponds to one and only one element y in the range. So every input or domain element corresponds to only one output or range element. If a function is defined this way, so that one range element has only one input that it's used with, then this is called a one-to-one function. Why this matters is because only one-to-one functions have inverse functions. So the definition of an inverse function is that if you have a one-to-one function to start with, then it has an opposite or inverse function. And it's denoted with this notation here. You read this as f inverse. And f inverse is the set of all y comma x. So this is an ordered pair where y is first and x is second. And then this line right here, you could read this as such that. So the set of all y comma x ordered pairs such that the ordered pairs x comma y belonged to the original function. So inverse or opposite, you started with x comma y as your inputs and outputs for your original function. So the inverse, what used to be the output is now the input, and what was the input is now the output. So x and y switch. So some facts about inverse functions. For a one-to-one function, each x value corresponds to one and only one y value, and each y value corresponds to one and only one x value. This is the whole idea of one-to-one that we just talked about. And if a function is one-to-one, that's when it has an inverse function. So this is like a necessary criterion. It has to be one-to-one for the function to have an opposite. And the reason is we want to go backwards. We want to do the opposite. And if it's not one-to-one, we can't go backwards. So over here, if you think of your domain of your function as the numbers you can plug into it, so I'll just have 3 here, x1, x2, x3, and the range is what comes out. Okay. Now, our original function, you take values from the domain, plug them into your function, and get out values from that we call the range. Now, the inverse function does the opposite. So you have to have exactly one input goes to exactly one output. And if it has this one-to-one relationship, one input gives you one output, that's when you can go backwards and you can do the inverse. So you can start with, let's say, y3, and you can plug it into your inverse function, and it's going to take you back to x3. And so the domain of the original function becomes the range for the inverse function, and vice versa. The range of the original function becomes the domain of the inverse function. So everything swaps. Now to review the graphs of the inverse functions, your graphs of f and f inverse, they do this nice reflection across this line, y equals x. So the diagonal line, y equals x, is this line right here. And this is like your mirror line. And so original function and its inverse function, the graphs will reflect across this line. It'll be mirrored across this line. So if originally you had a comma b as a point, that swaps and becomes b comma a. And then this is directly related to our definition for our inverse function. Y comma x is your point when x comma y was the original point. And so here's just an example of a graph and its inverse. The original is the blue, x cubed minus 3, and the inverse function is the cubed root of x plus 1. And notice the graphs. They do mirror each other across this line, y equals x. So this is true for all inverse functions and its original function. Now what we're going to be talking about is our trig functions and their inverses. And so what I want you to think about is that trig functions are not one-to-one initially. So we're going to do this thing called restricting the domain, and that's so that we can have one-to-one functions. So here's your sine wave, and now this is not a one-to-one function because the values repeat. For the x value of pi, you have the same output, 0, as an x value of 0. or negative pi or negative 2 pi. You're going to get the same y value, same output, for all these different points. So this function is not one-to-one. So what we do is we look at just a limited piece of this function. So right here in the middle, we're going to take our sine wave, our sine function, and only look at this part of it. And so we want our sine graph, our sine function, to be in between negative pi over 2 and positive pi over 2. And then this is going to be the restriction to make this function one-to-one. In this space here, this is going to have only one y value for every x value. If we limit what we look at, if we restrict this domain for negative pi over 2, that's the only time we're going to get out y equals negative 1. When we plug in 0, we get out 0. When we plug in pi over 2, we get out 1. So this is now a one-to-one function because of this restriction. All right, so our original functions, we have to restrict all of the domains in order to make them one-to-one functions. Now here is the information for how the domains are restricted. We limit the domain so that we don't have repeated outputs. So we just talked about the sine graph, the sine function. We only want x to exist between negative pi over 2 and pi over 2, which on your unit circle is quadrants 1 and 4. Cosine, we only want that to be considered for x values between 0 and pi, which on your unit circle is quadrants 1 and 2. And we do this for all 6 trig functions, all 6 circular functions. And by restricting this domain, what we're doing is we're making all of these functions one-to-one. For every single input, there's only one output that corresponds to it. Now, for our inverse functions, okay, these restricted domains, think inverse means opposite, these now become the range. Okay? And so notice the notation changed for our function. We now have inverse functions, and what was the domain is now the range. And so the new domains is what used to come out of your functions. So sine, the output was between negative 1 and 1 for every value you can plug in for sine. And so for sine inverse, that's what you plug in. You can plug in anything between negative 1 and 1 into sine inverse, and you're going to get an output. And the output will be between negative pi over 2 and pi over 2. Or in other words, angle values in quadrants 1 and 4. Very similarly, cosine inverse has a domain of negative 1 to 1, and that's because originally cosine, your output were numbers between negative 1 and 1. So now when you plug in anything between negative 1 and 1 into cosine inverse, what you get out is some angle value between 0 and pi, or angles between in quadrants 1 and 2. And then we have the same kind of idea hold true for all 6 of our trig functions. Okay, so just like I was mentioning, the domain and the range switch from the original function. What was the range is now the domain. What was the domain is now the range. Okay, so from algebra, you actually learn this process. Hopefully this is going to kind of remind you of some stuff you've seen. But to find an inverse function, you just follow these 4 quick steps. And for us, it's mainly going to be steps 2 and 3 most of the time because we're going to be working with y already. And step 1 is just to replace f of x with the letter y. And then step 4 is to replace y with the inverse notation. Okay, so we're going to mainly focus on steps 2 and 3. So let's work this out for sine inverse, or to find sine inverse. Okay, so y equals sine x is how we're going to see this most of the time. And then swap x and y. So now x is where y used to be, y is where x used to be. And then notice step 3 says solve for y. So you have to think about it for a second. How do you solve for y? When you're solving for something, you undo what's happening to it. So the question becomes, how do you undo sine? This is sine of y. How do I undo sine? Well, I apply sine inverse. The inverse will undo the original. And so you have to do the same thing to both sides of your equal sign. You apply sine inverse to the left side. You apply sine inverse to the right side. And so sine inverse of sine, these two undo each other. Something in its inverse undo each other. So what's left on the right side is just y. The sine inverse undoes the sine. And so this is our answer, but let's just do step 4. We're going to replace this with our inverse notation. So this is sine inverse. Now, most of the time though, we're going to probably just leave it with the y. So step 4 is kind of optional. We're going to leave it with our y notation. Okay, so let's focus on sine inverse, and then we'll go through all 6 of our inverse trig functions. So sine inverse, or another way to call this is arcsine. This is just preference, or your textbook might vary in how it's being said, or if you search online. Some people use sine inverse with this notation, some people use arcsine. They are the same thing, okay, so just be aware it's the same thing. The domain is from -1 to 1. The range, the output, is angles between -π/2 and π/2. And so this is what the graph looks like. And then if you were to use a graphing utility, this is what it looks like. So if you think about how we used to do this, and it's exactly the opposite. If you look at the outputs, we used to take sine of π/2 was -1. Sine of 0 was 0. Sine of π/4 was square root 2/2. Now what was originally the input is now what comes out. And so the input is what used to be the output. So what we used to get out of our sine function is now what we plug into our sine inverse function. So let's try this out. Find y in each equation. Part A, y equals arcsine 1/2. So this is sine inverse. So this is asking you about the following. Y is the number or angle in our given interval for sine inverse whose sine value is x. Okay, so it's saying sine of what angle or number equals 1/2. So you can rewrite it. You can say, well, sine of this angle y equals 1/2. And then this is the domain, okay, our restricted domain, which is our range at this point. Okay, so you want to think about your unit circle to figure this out. What sine angle, what angle do I have to put here for my output to be 1/2? Okay, so let's take a look at our unit circle. Now we don't want to look at the whole thing because we restricted the domain of sine originally to get the sine inverse. So we are only looking at quadrants 1 and 2. Now -π/2 is down here. Yes, it says 3π/4, but remember if it says a negative value or angle, it's just because we're traveling clockwise. So this is -π/2, all the way up to +π/2. Real quick, the reason why we say -π/2 to +π/2 is to make this continuous. If I label this as 3π/2, it's actually not continuous. I would have to start at 0, I'd have to go up to π/2, and I'd have to skip all this, quadrants 2 and 3, and then start at 3π/2, and then stop at 2π. So in order to avoid that, to make it continuous instead, I just call this -π/2, and I start at -π/2, travel up to 0, and then go up to +π/2. Okay, so we are thinking about which sine value in these two quadrants would be 1/2. And hopefully you're looking at it, looking for the y component of your quartered pair, which is right over here. Okay, so we're only looking at these two quadrants, and we're going to pick π/6 because that is the angle, our 30 degrees, that gives us a sine value of 1/2. And so since sine of π/6 is 1/2, that's our value for our sine inverse. So y equals π/6, or you can say arcsine 1/2 is π/6, or sine inverse of 1/2 is π/6, and that would be the answer. All right, taking a look at part B of this example, y equals sine inverse of -1. So y is actually the original angle. So we're thinking about sine of what angle gave us a value of -1. So you can rewrite this as sine of y equals -1. And then we're going to only look in our range here, which was originally our restricted domain. So we're only going to look from -π/2 to +π/2, or from quadrants 4 to 1. And if you think about your unit circle and you think about quadrants 4 and 1, sine is negative in quadrant 4, and sine is -1 at negative pi over 2. Or originally this was written as 3 pi over 2, but we're just going to write it as negative pi over 2. Like we discussed in the previous slide about keeping the domain here, or in this case our range, our original domain, continuous. So negative pi over 2, sine of that angle is negative 1, so sine inverse of negative 1 equals negative pi over 2. Part C, y equals sine inverse of negative 2, so you're thinking about sine of what angle gives you a value of negative 2? Well, nothing. So hopefully that kind of rang a little bell for you in your head. You say, wait, I've never seen that come out of a sine function, and that's because it won't happen. Negative 2 is not in the domain of the inverse sine function, which is between negative 1 and 1. Sine, originally, your sine function, if you plug in any angle into the sine function, you're never going to get something less than negative 1 or greater than 1. Sine values don't exist beyond this interval here. So this doesn't exist. So the answer you can say doesn't exist. If you try your calculator, it's actually going to give you an error message. It'll say something like domain error. All right, so just a quick note about the times that you might get an error. So be certain that the number given for an inverse function value is in the range of the particular inverse function being considered. Okay. So our inverse function values, the domain, the numbers we can plug in were the original range for the original functions. So the sine function never gave you values less than negative 1 or greater than 1. So when you go to plug these numbers, something outside of this domain into the function, the inverse function, you're not going to get an answer. You're going to get an error. So let me just show you something down here with secant inverse. So for y equals secant inverse, this was originally the range for secant, the secant function. So it's now the domain for secant inverse. So notice what this says. Numbers less than negative 1, negative infinity all the way to negative 1, or numbers bigger than 1. So if I try to plug in like 1/2 or 0 into secant inverse, I'm going to get an error. It does not exist. Now let's talk about inverse cosine. So inverse cosine function, you can read this as y equals cosine inverse x or y equals arc cosine x. And this is the number, so y is the number or angle between 0 and pi whose cosine value is x. Okay, so what used to be our input over here, the y column of our table, is now the output, and what used to be the output is now the input. For example, cosine pi over 2 equals 0, so cosine inverse of 0 equals pi over 2. And then this is the graph of cosine inverse, and then this is the graph if you were to use a graphing calculator. Let's find an example here for cosine inverse. Part A, y equals arc cosine 1. So this means cosine of y equals 1. So which angle for our restricted domain originally, which is now our range, between 0 and pi, which angle here is going to have a cosine value of 1? So this is quadrants 1 and 2. And so between quadrants 1 and 2, cosine of 0 equals 1, and so y is 0, or arc cosine of 1 is 0. Let's do part B. So part B says y equals cosine inverse negative root 2 over 2. So this means cosine of y equals negative root 2 over 2. Again, in quadrants 1 and 2. So you want to look at your unit circle and say, where do I have a cosine value of negative root 2 over 2 if I'm only looking at quadrants 1 and 2? And you'll find that that happens at 3 pi over 4. So because cosine of 3 pi over 4 is this value we were looking for, cosine inverse of that value, negative root 2 over 2, is the answer 3 pi over 4. Next, let's talk about tangent inverse. So y equals tangent inverse of x, or y equals arctan of x. The domain here is all real numbers, but the range is between negative pi over 2 and pi over 2. Now this one's the first one where we have asymptotes on our graph. So the graph of tangent inverse, there's actually asymptotes that we don't touch down here at negative pi over 2 and up here at pi over 2. So this range is really close to the range for sine inverse, except the parentheses let us know that we're actually never going to get the two end values. We never actually touch where these asymptotes are at. So we're never going to get pi over 2 or negative pi over 2 as an output for our tangent inverse function. All right, now let's look at cotangent inverse or arc cotangent. Very similar to tangent inverse, we have a domain of all real numbers, but our range here is very close to the range for cosine inverse, other than the ends not being part of it. So we can't ever get 0 or pi as an answer here. And we have asymptotes at pi. We also have an asymptote at 0 for this one. Secant inverse or arcsecant, the domain is anything less than -1 and anything bigger than 1 to include -1 and 1. And then the range, it's just like the range for cotangent inverse, except we can't equal this number right in the middle of this range. So we want quadrants 1 and 2, but we have to actually skip the value y would ever equal pi over 2. And that's because this would be undefined. And so here's your graph of secant inverse, and there is an asymptote right here at pi over 2, because you're never going to get that out as an answer for secant inverse. And then cosecant inverse or arc cosecant, same domain as secant inverse, anything less than -1 to include -1, anything greater than 1 to include 1. Now the range here matches with the range of sine inverse, except we can't equal this one value in the middle. So anything in quadrants 4 and 1, except right here at the middle of those two quadrants when y is 0. You're never going to get out y equals 0. There's actually an asymptote right here on your graph for cosecant inverse. Now we're going to try some examples, and notice we're finding these in degree mode. So if you do use your calculator, you want to make sure you're in degree mode instead of radian mode for this. So theta equals arctangent of 1. So this means tangent of theta equals 1. Now theta must be in between -90 degrees and 90 degrees, quadrants 4 and 1. And then if you think about what you're looking for which angle gives you tangent equal to 1. So since this is positive, that puts us in quadrant 1. So the angle we're looking for is in quadrant 1. So where in quadrant 1 do we have a tangent value equal to 1? Okay, so we're only looking at quadrant 1. Technically, tangent inverse is defined in quadrants 1 and 4, but notice we don't include the endpoints here. We're not including negative pi over 2 or positive pi over 2. It would be undefined there. So we get really close to these endpoints of these quadrants, but we don't include them. And then we're only focused on quadrant 1, and hopefully you remember where this would be at 45 degrees. Your tangent value, y divided by x, would equal 1. Okay, so arctangent of 1 tells us that tangent theta equals 1, and therefore that angle we're looking for is 45 degrees. Part B, we want theta where theta equals secant inverse of 2. So we want to figure out secant of what angle equals 2. Now, for secant inverse, our outputs would give us values in between quadrants 1 and 2. And now because this is a positive value in quadrants 1 and 2, we only actually look at quadrant 1 because secant is positive in quadrant 1. So thinking about your unit circle, you want to think about secant of what angle in quadrant 1 equals 2. Okay. Now, also for secant inverse, we have to exclude this value in the middle. If you plug in pi over 2 or 90 degrees in for secant inverse, it's going to be undefined. Okay? And so anything in quadrant 1 or 2 except for this middle value would work for secant inverse. And so we already know that we're looking for when we're going to get positive 2 out of our secant function. So we're limited here to quadrant 1. And then think about secant 1 over cosine, where we would get a value of 2. So hopefully you're looking right here. Here's our x value for cosine. So 1 over 1/2 would give us 2. And so secant theta equals 2 when theta is 60 degrees. So secant inverse of 2 is 60 degrees. Now let's do this again, another example, but this time with a calculator. So find y in radians, so back into radian mode, you want to change your calculator to radian mode, if y equals cosecant inverse of -3. So in radian mode, hopefully you realize, I don't know if yours does this, but most calculators don't have a cosecant button, let alone a cosecant inverse button. So instead, you have to use the fact that cosecant is 1 over sine. So cosecant inverse, you're going to use sine inverse, but you have to flip over this input, okay, because cosecant is the reciprocal of sine. So if you're going to use your sine inverse button, you have to flip over the argument. So instead of -3, -1 over 3. And you plug that in, and we get out -0.3398. Okay? And you can round this to however many decimal places you need. Part B, find theta in degrees if theta equals arctangent, or arccotangent, or cotangent inverse of -0.3541. Now this one we have to be a little bit careful about. So let's walk through this. Be careful when using a calculator to evaluate the inverse cotangent of a negative quantity, which is exactly what we're trying to do here. Inverse cotangent of something negative. So what we're going to end up doing is we're going to enter the inverse tangent. So we're going to use our inverse tangent button because most calculators don't have an inverse cotangent button. So inverse tangent of the reciprocal, because cotangent is the reciprocal of tangent, of the negative quantity. Now that's actually going to give us an angle in quadrant 4, which is not defined for cotangent inverse. So we're going to have to adjust because the calculator will give us an angle in quadrant 4, but cotangent inverse is not defined for quadrant 4. So to adjust, we have to add 180 or pi. So since inverse cotangent is negative in quadrant 2, then you just adjust your answer by adding 180 degrees or pi. So think about the outputs for our inverse functions. For cotangent inverse, the output would be in quadrants 1 and 2. Okay? Now, we don't have a cotangent inverse button on our calculator, so if we're going to use our calculator, we have to adjust. We're going to use our tangent inverse button, which gives us answers in quadrants 4 and 1, excuse me. So I have to adjust the answer that my calculator will give me in order for me to get answers in quadrants 1 and 2. Okay, so now we know our value that we're plugging in is negative, so that's going to have us focus on quadrant 4 because a tangent value here would be negative. Okay? And so if we get an answer in quadrant 4 for tangent inverse, we add 180 to that, or pi, and that will give us the correct angle we need. It'll give us a value in quadrant 2. So that's what the adding pi or 180 is about. We take answers from quadrant 4, we add 180 or pi, and it'll give us answers in quadrant 2, which is where cotangent inverse was defined. Okay, so let's work this out. Now the restriction on the range for cotangent inverse means that our answer needs to be in quadrant 2. So we use our tangent inverse button. We take the reciprocal of our input because we actually are interested in cotangent inverse, not tangent inverse. This answer would be in quadrant 4, so then we add 180 to get the correct answer, which is about 109.49 degrees. In this next example, we're going to be evaluating expressions without a calculator. And the way we're able to do this is that we actually don't need to know the angle, and here's why. Tangent inverse of anything would give us an angle, but then what we're interested in is sine of that angle. So we really don't need to know what the angle is, and I'll work this out with you so you can see why. This represents an angle tangent inverse of 3 pi over 2. We're going to call it theta. So theta is tangent inverse of 3 pi over 2, meaning that tangent theta equals 3 pi over 2. And now tangent inverse, or arctangent, we know it's defined in quadrants 1 and 4. Since we're given a positive tangent value, 3 over 2, we're going to focus our attention on quadrant 1. Now we're going to sketch a triangle in quadrant 1 in order to figure out what we're looking for, which is eventually going to be the sine value of this angle. Okay, so based on the fact that we knew what tangent inverse of theta was, it was 3 pi over 2. Remember, tangent is opposite over adjacent side for our triangle. So this means that for our triangle here with angle theta in this corner, this side's 3, this side's 2, and we use Pythagorean theorem to get our hypotenuse, which is square root 13. Then the question was, well, what is sine of tangent inverse 3 pi over 2? In other words, what was sine of theta? And we have our triangle, and we can figure this out. So sine of theta is just going to be opposite side over hypotenuse, and we end up getting 3 root 13 over 13. Let's try part B. So same idea as the part A we just finished. Cosine inverse of negative 5/13. This is an angle, and then eventually we want tangent of that angle. Okay. So we're going to call that angle A. So this part here is the angle A. So if cosine inverse is negative 5/13, we know that cosine A, cosine of that angle, equals negative 5/13. And we're going to use a triangle like we did on the last example. So first let's recognize that cosine inverse, or arc cosine, is defined in quadrants 1 and 2. And because we have a negative cosine value, we're going to focus on quadrant 2. And then we're going to draw our triangle in quadrant 2. Okay, so based on the fact that we know cosine inverse is negative 5/13, cosine is adjacent side over hypotenuse for our triangle, so we fill in our given values, and then we use Pythagorean theorem to find our opposite side, which is 12. And then the question was, what is tangent of this? So tangent of this angle A, tangent is just opposite over adjacent, so negative 12/5. Let's try this example now. Also evaluating an expression without a calculator, but this time it's a little different because we have two angles going on inside this argument of cosine. So arc tangent of root 3, this is an angle, and then plus arc sine of 1/3, also an angle. So this is cosine of the sum of two angles. So we're going to have to work with both of these. All right, let's call the first angle A and the second one B. And so arc tangent of root 3 equals A means that tangent of A equals root 3. And then arc sine of 1/3 equals B, meaning that sine of B is 1/3. Now we're going to sketch both angles A and B and then their triangles associated with them. And they're both in quadrant 1. They are both positive, and arc tangent is positive in quadrant 1 and arc sine is positive in quadrant 1. From our given information about the inverse functions, we know that tangent of our angle A is root 3. Rewrite that as a fraction, square root 3 over 1, and this is going to help you draw your triangle. For sine B, we know that that should equal 1/3, and so our triangles look like the following. Tangent of A was root 3 over 1, so opposite over adjacent, and use your Pythagorean theorem to find out that the hypotenuse is 2. For angle B, we knew that tangent was 1/3, so the opposite side was 1, and the hypotenuse was 3. And again, using Pythagorean theorem, we have that our adjacent side, the missing side, was 2 root 2. Now that we have these two triangles drawn, we're going to actually find 4 values. What we need is sine and cosine of angle A, as well as sine and cosine of angle B. And the reason we need all 4 of these is because what we're working with originally is the sum of angles, and so we're going to use one of our formulas that we previously learned, so we actually need all 4 of these numbers. we have the cosine of a sum, which was an identity we learned a couple sections back. I think 5.3 if you want to look back at that. So cosine of a sum identity. And cosine of a sum, angle A plus B, this was our formula. This equals, from our formula, cosine A times cosine B minus sine A times sine B. And we just figured out all four of these numbers, so now that we reference our formula, we plug this in. And so we fill in our four values we just came up with, and then our final answer, 2 root 2 minus root 3 all over 6. We're going to do part B, evaluate the expression again without a calculator. Notice what we're finding, tangent of 2 arcsine 2/5. So this inverse sine right here, this is an angle. So this is really saying tangent of twice an angle. So we're going to refer back to our double angle formula here. So let's call this angle for arcsine theta. So this arcsine 2/5 equal to theta implies that sine of theta is 2/5. And then we'll use our double angle identity for tangent, which we learned in a previous section. Tangent of twice an angle theta equals this expression here. Now we're going to sketch our angle and corresponding triangle in quadrant 1 because it was positive arc sine value and arc sine is positive in quadrant 1. Okay, so using the Pythagorean theorem and the fact that arc sine was 2/5, this is our triangle associated with our angle theta. So then the question was, what's tangent of twice theta? But we actually only know tangent of theta right now. So this is not tangent of 2 theta yet. So tangent of theta is opposite over adjacent. So 2 square root 21 over 21. Now we still have to use this in our double angle identity. So referring back to our double angle formula, we now know what tangent theta equals, so we plug that in. So where there's a tangent theta, we put in what we just figured out, 2 square root 21 over 21, top and bottom. On the bottom it gets squared, on top it just gets multiplied by 2, and we start simplifying. Okay, so this is just from squaring. Okay, you squared away the radical on the 21 on top here. The 2 got squared to make 4, and then 21 squared on bottom. Then keep simplifying just a little bit. We end up with 4 over 21 in this bottom fraction down here. And then common denominator, this whole denominator becomes 17 over 21. And then flip and multiply and simplify to get 4 root 21 over 17. Now in this example, this one's going to be a little bit different. We're told to rewrite or write sine of tangent inverse of u as an algebraic expression in u. So what I want you to notice is that we don't know any numbers here. We have sine, we have tangent inverse, we have u, but u just represents a number and we don't know what it is. So in order to work this out, we're going to end up with u in our answer, and that's exactly what we're told to do, expression in u. Now tangent inverse represents an angle theta, so if we call this tangent inverse of u theta, we know that tangent of theta equals u. Now because we don't know what u is, whether it's positive or negative, it could be either one, we have to account for both. And tangent inverse is defined in quadrants 4 and 1, between negative pi over 2 and positive pi over 2. So we're actually going to sketch 2 triangles, one in quadrant 1 and one in quadrant 2, to account for whether tangent was positive or negative. Alright, so here's our 2 triangles. And now what I want you to just realize where these values came from. I'll break it down real quick for this triangle in quadrant 1. We knew that tangent of theta was u. You can think of u as u over 1, u divided by 1. And so tangent is opposite side over adjacent side, so that's where this 1 came from. Opposite was u, over adjacent was 1. And then using Pythagorean theorem, you would take u squared plus 1 squared, and you would get the hypotenuse squared. But if you don't want the hypotenuse to be squared, you just square root it. So that's why we have square root u squared plus 1 as the hypotenuse. Then we go back to our expression. Sine of tangent inverse of u. Well, tangent inverse of u is what we're calling theta. And then sine of theta, we just look at our triangles that we drew. Here's theta. Sine is opposite side over hypotenuse. So u over square root u squared plus 1. And if you want to, you can rationalize this denominator. Let's try one last example here, similar to the one we just finished. Write cosine of 2 sine inverse of u as an algebraic expression in u. So here's our angle, sine inverse of u. We're going to call that our angle theta. And so sine of theta equals u. And now thinking back to our expression here, noticing what we're working with, this is cosine of 2 times this angle u, or theta, excuse me. So we're going to use a double angle identity. We know this from a previous section. Cosine 2 theta, twice an angle, equals, we had 3 expressions that we learned. This was one of the 3, equals 1 minus 2 sine squared theta. And so we're going to use the fact that we know what sine theta is. It's u. So we're just going to replace sine theta with u. Okay. So cosine of 2 sine inverse of u, this is what we called theta. So this is just cosine 2 theta. Here's our formula from what we just wrote down. And so sine theta is u. So right where there's a sine theta, write u, and that's our answer.